Welcome to this continuation of these webinars on functional analysis. And let us talk a little bit about a quick review on matrix spaces. And let us start by looking at what is a matrix space, okay? What defines a matrix space? And in order to really appreciate the definition of a matrix space, we need to go back to the historical development of what brought us to the concept of matrix spaces. So at the origin, of course, we had geometry. And geometry, we have R2, the geometric plane, or R3, the geometric space, or the space as known as the space. So obviously, if we look at the Euclidean geometry, the classical geometry, for the purpose of what I'm going to be talking about here, I can basically focus on R2 and drop R3. The ideas are basically the same whether you go for R2 or you go for R3. Once you get the idea, then it doesn't matter. So here, what we learned in baby geometry is that if you take 2 points, A and B, in R2, okay, so the distance from A to B is the square root of XA minus XB squared plus YA minus YB squared. So this is what's known as the Euclidean distance, and we have this distance between 2 points. So of course, armed with this distance, R2 has some very beautiful properties, and we learned them over the years when we started learning about geometry and the properties of the plane or the space, in fact. But here, let us look at it from a different point of view. What are some of the properties that the distance d here are satisfied by the distance d, and really they are the minimal properties that you cannot, for example, ignore. And some of the fundamental properties are, number one, that if the distance between A and B, the 2 points, is equal to 0, so it's a positive number first. The distance is a positive number, okay? And that the distance is equal to 0 if and only if the 2 points are the same, okay? In other words, XA equal XB and YA equal YB, okay? That's number one. Number two, okay, it is obvious that the distance from A to B is the same as the distance from B to A, because the squares with the minuses, if we take XB minus XA, is going to be the same. So what in fact this number two implies is that when we talk about the distance from A to B, we can easily say the distance between A and B. In other words, it doesn't matter which one you're starting with and which one you end up to. So if we say the distance from A to B, it means that the distance from B to A is different than the distance from A to B. But if you are convinced that the distance from A to B is the same as the distance from B to A, then in this case we can talk in English. We can say the distance between A and B without being precise here, from what to what. Okay, so that's known as the symmetry of the symmetric property of the distance. And the next one is a little bit tricky. Really, the next one is tricky. And in fact, it is known as the triangle inequality. And the reason why we call it the triangle inequality, it has something to do, from a purely geometric point of view, of the triangle. So if you take 3 points, A, B, and C, and you look at to that triangle, then the distance from A to B, this is just a geometric property. So the distance from A to B is less than the distance from A to C plus the distance from C to B. And of course here you can have any kind of combination, and still, like for example, the distance from B to C is less than the distance from B to A plus the distance from A to C, etc. So this inequality, in fact, can be used to tell the student, can an example, okay, baby geometry example, is there a triangle, okay, on the plane, such that three numbers, okay, such that A, B, C, three numbers are the length of the sides of the triangle, okay? And you can, for example, if you take, for example, okay, if we take A, B, C equal 2, 3, and 5, okay, then it's obvious that the answer is yes, okay, we can, okay, or for example, even we can have 1 just for the sake of, okay, then you can check, sorry, not 1, no, not 1, 2, 3, 1, 3, yeah, 2, 3, 5 will work. Why? Because if I take 3 plus 5, it's 8 bigger than 2, 2 plus 3 is 5, greater or equal than 5, and finally 2 plus 5 is 7, bigger than 3. But if I take A, B, C equal to 1, 5, and 9, the answer is no. Why? Because if I take 1 plus 5, 6, is not bigger than 9. So there is no way we're going to find a triangle where the length of the sides is 1, 5, 9, but it is possible for 2, 3, 5. So this is just to show you how this triangle inequality is a pure geometric property, okay? Now, building on this, so as you can see, these are basically, over the years, these are the three main properties that defines the minimum one defines a distance. So then people offer the following definition. So definition, let x be a set, okay, a function d from x cross x into, it has to be positive, okay, is called a distance, as called a distance on x, if and only if we have the three properties. Number one, that the distance of x and y equals 0, if and only if x is equal to y, and x and y are pointing the capital X at. 2, we have symmetry, the distance x to y equals the distance from y to x, and finally we have the distance from x to y is less than the distance from x to z plus the distance from z to y. That is the triangle inequality. So, and if we take the pair at Z is called metric space. Is called a metric space. So a metric space is a combination of a set and the distance defined on the set between the element of the set. Okay? So sometimes if there is no confusion, people drop the D and they will say the metric space X, okay, or M. But what do they mean is in fact a pair, a set with a distance, because you may have different distances. And you will see in subsequent web notes that there are easy examples where you have different distances. Let me just make a comment here, Mark. Okay, when you are given a set X, given a set X, and you are looking at a distance on X, and so given and D defined on X into 0 plus infinity, for example. And the question is to check if D is a distance. Okay, check. The question is check that D is a distance. Okay. In general, Okay, the hardest part is number 3, the triangle inequality. Not the first one, not the second one. Usually the first one and second, meaning when you have to 0, then the points are equal, or the symmetry are easy to see. But the third one is difficult to see. And sometimes it takes some hard work to do to show that you have the symmetry. So let me give an example now of this, a beautiful example that shows also that you may have more than one distance defined on a matrix space. For example, let let xd be a metric space. So d, in this case, d is a distance defined on x, okay? And consider the new function, okay? Let rho defined from x into 0 plus infinity, defined by rho of x, y equal distance from x to y over 1 plus distance of xy. Okay, so this is positive, and it's not very hard to see that it's well defined, and that number 1 is well defined. Number 1 is well satisfied. Why? Because if rho of xy is equal to 0, then d of xy is equal to 0. And the symmetry is also inherited from D. And the hard part is triangle inequality. In other words, we need to prove that rho of xy is less than rho xz plus rho of zy. Okay? And for any point x, y, and z in M, this is not obvious, and this needs a little bit some hard work. As I said earlier, the triangle inequality is always the one that gives the people the hardest time. So in this case, in order for us to appreciate what's going on, let me start first by introducing a real function. Let f of t defined by t over 1 plus t, and this is defined on 0 plus infinity, for example. Okay. Okay, so if we take this function, it's easy to see that the derivative of this function is positive. It's equal to 1 over 1 plus t squared. So it's increasing. First of all, we have f0 equals 0. ft is increasing. And one more property, which is amazing, is that f satisfies if subadditive. F of t is subadditive, meaning that f of a plus b is less than f of a plus f of b. Okay? And to convince you with this property, okay, let us prove it. Let a and b be positive numbers. Okay? We want to show that a plus b over 1 plus a plus b is less than a over 1 plus a plus b over 1 plus b. And for that, this quantity is well defined. This is equal to a over 1 plus a plus b, b over 1 plus a plus b. Okay? And it's obvious and clear that a over 1 plus a plus b is less than a over 1 plus a because we're making the denominator smaller, therefore the fraction becomes bigger, and b over 1 plus a plus b is less than b over 1 plus b. In other words, we have what? We have a plus b over 1 plus a plus b less than a over 1 plus a plus b over 1 plus b. So f is indeed subadditive. Armed with this function f, see now that rho of xy is f of d of xy. Okay? And because of the triangle inequality, we know that f is increasing, so we have rho of xy is, since d of xy, I mean the triangle inequality satisfied by d, is going to be less than f of d of xz plus d of dy. This is the triangle inequality satisfied by d, and the fact that f is increasing, combined with f being a monotone increasing function. And now we use the subadditivity. This is less than f of d of xz plus f of d of zy, which gives me what? That this is rho of xz plus rho of zy, which is that's what? The inequality, or the triangle inequality for rho. So now we have this set, we have the distance d, the original one, and now we have a new distance rho. Okay, rho has some nice properties, like what? Like rho is less than 1, it's always less than 1, so what we call a bounded distance. But in any case, this shows us what? That number one, on a set we may have more than one distance. Okay? That's number one. Number two, in this example, I tried to show you that if I change f now to another function which satisfies the same properties, meaning, let's say h of 0, h is defined on 0 plus infinity, and h of 0 is equal to 0. In other words, the following property is, okay, f of 0 equals 0, h of t is increasing, and the subadditivity, then you can generate a new what? Distance. So this is a very, very, very interesting. But at the same time, as I said earlier, the hard part always in proving that something is a distance is to show the triangle inequality. That is the hard part. One more thing, one more example is that shows that in fact, let me put it as a remark here, okay? It's interesting to know about this, but it's not like something that's going to make us, gives us deep understanding or deep knowledge, but it's something that's good to know. So here, if we take, if x is any set, take any set, okay, and define the function d on x cross x into 0 plus infinity in the following way. The distance from x to y is either 0 if x equal to y, and 1 if x is not equal to y. So as you can see, this is a well-defined function on the element of x. And it's not very easy, I'll leave it to you, to show that in fact d is a distance. Okay? We call it the discrete distance. It's a distance, okay? Distance, okay, known as the discrete distance defined on x. So what does it tell us this remark tells us that in fact any set can have the structure of metric space. The problem is that this discrete distance is useless. It doesn't bring us some deep knowledge or deep information on the structure of x. Okay? And that's why people do not use it. So it's useless. The next example that I want to mention, and I want the student to be aware of, not that it's going to be useful in the case of functional analysis, for example, but it's good. It's a very, very powerful example, for example, in artificial intelligence, as well as logic programming, and also in economics. So the following example, what's known as ultrametric spaces. Ultrametric spaces. So what does it mean? What is this? It means you have a metric space, just a metric space, okay? Okay, is ultrametric, provided that d satisfies the following, like that d of xy. In other words, there is an easier form of the triangle inequality, is the maximum of the distance from x to z and the distance from z to y. It's obvious, of course, that the maximum is less than the sum, and therefore this will lead to the triangle inequality. This is a little bit a stronger property to be satisfied. And as I said, metric spaces which are ultrametric, they have some beautiful properties. Like, for example, any triangle is an isosceles triangle, which is weird because in geometry we know that there are triangles that are not isosceles. It enjoys some very beautiful properties. So it's good that students or people are aware of this kind of distance and some of the properties of this distance. Clearly, as I said, the Euclidean distance in R2 or R3 is not an ultrametric distance. Okay. What we are going to be discussing next, not in this note here, is to talk about the concept of topology, okay, in metric spaces, as well as some beautiful theorems in metric spaces. Thank you for your attention.